Hello, everybody. Chloethedev here. So I've been meaning to go through the Ethereum yellow paper for a really long time. Pretty embarrassing, actually. I've never gone through the Ethereum yellow paper. I've never gone through the Ethereum any papers. I've always just listened to conference talks and gone into the Ethereum like research forums, and I've never actually taken the time to go through the papers. And uh, after my internship with HashCloak, one of the main things I've realized is that I learn really well from just going through and reading the papers that people have taken the time to do all the research for and put together. They have PhDs, or usually, or they've studied how to put together this information, and they're trying their best to do so in an understandable way. So this is taking the Ethereum yellow paper, which is quite a complex document, but it goes through the technical specifications of Ethereum. Um, and this takes it and breaks it down even more into layman's terms that anyone can understand. So I was talking with a group of people doing some art NFT stuff, and Rogan X, one of the artists and coders I was talking to, suggested reading the beige paper. I didn't know about the beige paper. I knew about the yellow paper, but I was like, you know what? Let me go through the beige paper. Let me see what it's all about. So I was reading it at the dog park earlier with Mika, um, and I got through most of it. Actually, I got to chapter 3, and I realized I might as well do this live because then at least I can go back when I forget what happened and remember it. Also, if someone else happens to happen upon this, they might learn that at least as a Ethereum beige paper to go read. Watching me go through it probably won't be that helpful. But um, yeah, I guess Micah Dameron wrote this. So thank you to that person. I appreciate it because it was actually quite easy to go through. So I'm just going to go through it. Um, Obviously, if someone does have questions, feel free to ask. Um, but I might not really be looking at the questions area. It's more just me going through the beige paper. Feel free to follow along or whatnot. I guess I'll put the link to it in the comments so that if anyone really wants to go through it yourself. That's probably most helpful. I'm just going to be going through it here, so I have it for later. So, abstract. The Ethereum protocol is a deterministic but practically unbounded state machine with two basic functions. The first being a globally accessible singleton state, and the second being a virtual machine that applies changes to that state. This paper explains the individual parts that make up those two factors. So, for me personally, what got me so interested in Ethereum as a whole was, I guess, that first part. Just a globally accessible state, like just one state, everyone knows what it is for 15 seconds or so. We all know what the state of this machine is, this computer. I think that's a really cool thing. And so imagining Bitcoin as a computer. So Bitcoin, most people know what that is when they talk about cryptocurrency, use very, very secure transferring of funds back and forth. So imagining Bitcoin as a computer, Ethereum uses that distributed ledger model to repurpose it into a virtual computer, giving machine level opcodes the same level of certainty as Bitcoin transactions. So where on Bitcoin, you're very, very, very secure about one thing. If you have assets and you want to send someone else assets, you are very, very secure cryptographically that if you have 5 Bitcoin, you send them 2 Bitcoin, you know that after a Bitcoin block or a certain amount of work has been done on that block, you know that you'll have 3 and they'll have 2, which is a very useful thing. I agree. But what Ethereum is trying to do, or what it does do, is takes a bunch of computer codes and gives them that same level of certainty. And so obviously Bitcoin Max would say that Ethereum doesn't have the same level of security as Bitcoin, and I would arguably potentially agree. But the point is, you're taking that level you're taking the security Bitcoin has, and you're trying to make it more useful. All this electricity we're using to secure the Bitcoin chain, why not use it to also not only be able to use to send back and forth transactions, but also be able to do other full Turing compete operations. So basically, just as you can be certain the Bitcoin ledger is accurate and that the timestamps are correct for the Bitcoin consensus mechanism, just so sure is it that machine instructions initiated on Ethereum will execute. In other words, programs executed on the Ethereum blockchain are basically unstoppable. This does not mean that Ethereum programs can't have bugs. A lot of them obviously do have bugs. This means that Ethereum programs can be trusted to execute without any interference from external non-network forces. This property arises from the inherent security of the blockchain, which is built by and maintained upon cryptographic proofs. So, I mean, obviously, through and through, you're just building upon cryptography. That's why you have so many different blockchains that exist these days. But you really have to look at like what is securing this new novel blockchain people are coming out with. Not all blockchains are the same. I mean, definitely not. Currently, there's a few blockchains that I have my eyes on that are not just Bitcoin and Ethereum. Like the Near blockchain, I want to learn more about them, but what they're doing, not Cello network, Cello. I want to look into what they're doing with a few interesting chains that I want to look into. But so 1.1 native currency, because Ethereum strives not primarily at the currency application, but at all applications, there's a fundamental network cost unit used to mitigate the possibility of abusing the network with excessive computational expenditures. This is called gas, and is explained fully in chapter 3. Gas is paid for exclusively in Ether, which is the smallest unit of currency. The smallest unit of currency in Ethereum is Wei, which is equal to 10 to the power of negative 18. So that little 3-line thing stands for ETH. That's why you see the little 3 bars of ETH. And yeah, Wei is 10 to the power of 18 zeros, 18 decimal places back, 1 Wei. Basically just saying that if transactions were free, people would abuse that and it would clog the network, and then the network would cease to be usable. So you have to price operations, opcodes, adequately to ensure that whatever the gas cost of a certain operation is not going to overload the network. The Ethereum network is subservient to others in terms of one thing only: Ether, the native currency for Ethereum. Everything that it can do is bounded up in its ability to expend Ether in exchange for gas, which buys a particular amount of system performance in some desired direction. So if you have Ether, which is some economic security for the network, you can spend that Ether in forms of gas to get things done. Cool. And a little chart of, what you could see done, whatever, not that important. Chapter 2, world state. The world state is a mapping of Ethereum addresses to accounts. Such a mapping consists of 2 things: addresses and account states. So very simply, the entire Ethereum blockchain is simply account addresses, or, currently you have account addresses and contract addresses, soon to be hopefully only just one type of address, because why would you want 2? It doesn't make sense. Anyways, and the state of those accounts. So obviously, if it's just a user account, it would only have the state of balances. If it's a contract account, it would have could have balances or storage or other kind of data. And then through the use of recursive length prefix standard RLP, this information is stored as a Merkle-Patricia tree. That's where you get into the computer science stuff, but it's not that complicated, actually. They're changing the trees from Patricia tree to from a Patricia tree into a binary tree soon, hopefully. But again, this is from Ethereum, like what it was or what it is now, not what it's going to be. But that's what makes it the backend. So the backend is just one big Merkle tree. Where you can go in and easily figure out what state you need to find. As a whole, the state is the sum of the total database relationship in the state database. So now you can look at this diagram. Does a very good job explaining what Merkle Patricia trees are, how they're used in Ethereum, and all the definitions to the side. So I mean, I love this paper so far. Anyways, 2.1.1. Merkle Patricia trees are modified Merkle trees where nodes represent individual characters from hashes rather than each node representing an entire hash. This allows the state data structure itself to represent not only the intrinsically correct paths in the data, but also the requisite cryptographic proofs which go into making sure that a piece of data is valid in the first place. In other words, it keeps the blockchain valid by combining the structure of a standard Merkle tree with the structure of a radix tree. Since all searching and sorting algorithms in Ethereum must be filtered through this stringently correct database, accuracy of information is guaranteed. Basically, you're using a very strict data structure, and then having cryptographic hashes and ways of finding things to make sure that if every time you need anything to happen, it needs to like be valid in this tree, then you know that if it's not valid in the tree, it can't happen. And so if something happened, it's valid in this data structure. So and you could the whole idea is you can easily search through the data structure. That's like the only like I guess the beautiful part of this is that it's easy to like see to validify. Yeah. So yeah. So the following searching tree beginning with hexadecimal values A and 4. So you can see the tree. But this is what I thought was really cool, the tree terminology. Like this is really what helped me. So the root node is this top node here. The child node is a node directly connected to another node when moving away from the root. So this is what helped me understand like Merkle trees in such explicit detail. So this would be a child node of this root node. This would be a child node of this node here, so on. You have a parent node, so this root node would be the parent node of this, and this would be a child node of this, the parent node, so on. Sibling nodes, a group of nodes with the same parent. So if this is the parent node of these two siblings, again, this is the child of this parent, so on. A descendant node is any node that is reachable by repeated preceding. Dude, a descendant node is anything below a parent, just like normal humans. Sometimes this wording just doesn't make any sense. An ancestor node is the other way around. So this node would be an ancestor of this node. All of these nodes here are ancestors of this node here. A leaf node is a node with no children. So that kind of, when I was reading papers like over the summer with Hashcloak, that would always confuse me. Like, what's a leaf node? I don't understand. Like, I assumed it was the last node, but it's nice to like know. Okay, yes, this is a leaf node. A leaf because it's dangling without any connections to it. A branch node, a node that at least one child. So this would be a branch node because it does have a child, has a leaf on it. So a branch has a leaf, makes sense. A degree is the number of subtrees of a node. So this is where it can get confusing, but this node has I think I would assume I would say two subtrees. I don't know, degree 2. This potentially has 3 subtrees. You're gonna have to come into the comment section and correct me if I'm wrong because I don't know. But like the degree of the polynomial, like the degree of the nodes, I read it a lot when I read research papers, and that's one thing where I would say I don't really know. The connection between one node and another is the edge. So there you go, super simple. The path, sequence of nodes, the edges connect to a node and descendant. So again, very simple, that will be the path. The level is 1 plus the number of connections between the node and the root. That sounds super complicated, but you just count these connections and add 1. So the level of the node is 1 plus the number of connecting the node and the root. So if you have this node here, this is a connection. These are all connections. So you're looking at kind of the connection to the node and the root. So this is the node. Let's say we're looking at, this is the root, 1, 2, 3, 4, and then 1 plus that, so 5. This is the 5th level. I guess you're counting backwards. So 1, 2, 3, 4, 5. It's also the 5th node. So I don't know. However, it's easier to remember. Doesn't matter to me too much. Node height. The height of a node is the number of edges on the longest path. So I think that's where you get like the difference between level and node height. Is this the longest path you're looking for? And that's where I guess things could be a little bit confusing. But I think what's important with node height is when we're looking at, say, the longest time to validate a certain proof would be, I would suppose, if you were very, very, very deep into the tree and you wanted to verify everything, I guess you'd have to go to the complete bottom of that tree. Whereas potentially, if your node is at like higher up in that tree, you might only care about where you are in that tree. Whereas if you're trying to validify the entire state of Ethereum, you might need the actual all the node heights of everything. So the tree heights. You might need to know the tree height in general, which is just the root, and then the highest. The height of the trees, the height of the root node. So you're looking at always the root node compared to everything else. The depth of node is the number of edges from a tree's root node to the node. This is all. And then I didn't understand what forest was. Like a forest is a set of n is greater than or equal to 0 disjoint trees. Like, I don't care what a forest is. Anyway, I've never even heard of forest before when I've read newspapers. So when I come across it, maybe we'll care about it again. Anyways, moving on. I think that's super cool. Anyone who wants to like learn more about like this like needs to be screenshotted and put like everywhere for like before you go through research papers because it's super helpful. Anyways, recursive length prefix encoding. This actually helped me a lot to understand like why it was so cool to have the data structure like that in Ethereum. So recursive length prefix encoding (RLP) imposes a structure of data that intrinsically considers a prefix text value to position the data in the state database tree. This text value determines the depth of a certain piece of data. There are two types of fundamental items one can encode in RLP, recursive length prefix encoding. One, strings of bytes. Two, lists of other items. So yeah, we'll just keep going because it doesn't even matter yet. RLP encodes arrays of nested binary data to an arbitrary depth. It is the main serialization method for data in Ethereum. RLP encodes structure of data only, so it does not pay heed to the particular types of data being encoded. So I think this is kind of cool. And what I take from this only is it's important because you can just throw whatever kind of data. It just generalizes all the data and makes sure you can find it quickly. It doesn't really care what data you're trying to find. It just makes sure that you can quickly search it, check if it's the same. Does the hash match? Good. If not, then it's just wrong. So you can just very easily compute the proof of that, or not you, but like your client, I guess would. So positive RLP integers are represented with the most significant value stored at the lowest memory address, big endian. And I've never heard that. I've read about this number or whatever, okay? But like, I've never heard it out loud, okay? So bear with me if I'm mispronouncing words in the paper. I'll probably look it up later, but and without any leading zeros. As a result, the RLP integer value for 0 is represented by an empty byte array. I think that's important too because if you want to know something 0, you can easily just search is array empty, and then boom, you know that it's very easy to search. If a non-empty decelerized integer begins with leading zeros, it's invalid because you know the RLP is, where is it? Without leading zeros. So it's very easy to check the validity because first of all, if it's empty, there's nothing there. Second of all, if there's zeros in front, then throw an error, like it doesn't work. Then you know it's only going to work if there's something in front that's not 0. So again, simplifies things a little bit when in terms, I don't know how simple it is, but simplifies things a bit. The global state database is encoded as an RLP for fast traversal and inspection of data. RLP encoding creates a mapping between addresses and account states. Since it is stored on node operators' computers, the tree can be indexed and searched without network delay. So again, you're holding the state on your personal computer and you don't need the network to do it, but still it would be difficult if to search every proof. You need a very powerful computer. By having it done this way, you can retrieve the data even on, like, I have a 2000, some old computer I'm running the Ethereum state on, or Ethereum, a node on, and like it can still run and compute, I guess, in part because of these enhancements, which is pretty cool. Not important. Anyways, now going to the block. The block is made with 17 different elements. The first 15 elements are part of what's called the block header. And this is what you would be learning about when you're like a blockchain developer or whatever, like what goes into each block. How do you and I guess even for searching what is that? So you found a block, an Ethereum block. What is in this block? How do you read it? So you have the parent hash, which is the KEKAK 256 hash of the parent block's header. That's just a hashing algorithm. So just KEKAK, I always spell it wrong with 2 Ks and then a C at the end. Anyways, so you're just hashing the parent block's header. Then you get Omer's hash. This is the KEKAK 256 hash of Omer's list portion of this block, which you'll see down here. These are Omer block headers, which is just all of this. And then, don't even worry about it. Just that's the second thing that's in there. Don't worry about it. The beneficiary is a 20-byte address to which all block rewards are transferred. So if you're a miner, you find this block, that would be you who gets the rewards. You could send the rewards to someone else, obviously. So this is just showing you that when you mine a block and you find it, you can send the rewards to someone else if you wanted to. State root I think you can send the reward to someone else. I'm like pretty sure. Anyways, this is the characteristics hash of the root state, so the root node of the state tree. After a block and its transactions are finalized. So we go up here, we're talking about this root node up here. So you have to find that root node. So you need to find the state root. So it's a hash, so it can't be changed. So you can find it. Pretty simple there. And then, sorry. You have the transactions root. This is the hash of the root node of the tree populated with each transaction. Sorry, so that's where I was. So you have the state root and you have the transactions root. So the state root is just like the state, the root of the state, so you can find it. The transactions root is after all the transactions are in the block. Because when you have transactions, it doesn't really matter the order. As long as you have all the added up hashes together, it'll be the same hash when you've hashed them, right? So if you have like the word cat and the word ball, and you hash them with cat 256, you get some random hash. But if you put ball, whatever order you put ball and cat, you still get the same hash. So this transactions root has all the transactions in that block or whatever, and it just wraps them up all into one hash. And you have the receipts root. This is the hash of all of the root node of the tree, populated with the receipts of each transaction. Again, this is just so you could easily verify things. So if you need to verify the transactions, it's like, was my transaction in this block? You'd go here, and you'd be able to put all the transactions together. Actually, there's probably some really cool stuff you can do where like you can easily just take what your transaction was, hash it, take all the other transactions, and you could like just do a zero out of like. I don't know how they do it in Ethereum, but I guess you would zero out, and you know that if your transaction wasn't included, you get back like a zero, and if it was, you get back a 1 or something like that. But anyways, you have the logs bloom, which is the bloom filter composed from indexable information, log address, and log topic contained in the receipt for each transaction in the transactions list portion of a block. So I think Bloom filters are pretty funny, only because there was like an ICO for this project called Bloom, like, I don't know, 2017, I don't know when. My uncle was super into it, I don't know who it was from. Some researchers are from university, some Ivy League school. But I was like, then after learning what Bloom filters were and I was like, okay, it's just data structure. Like, why would you, I don't know, it's just weird. But like, and then they have nothing to do with, they probably use Bloom filters now. But they do like KYC stuff now, and I'm assuming they use Bloom filters to keep the data secure and whatever. And I'm sure they'll do well because I was at McDonald's today actually, and it was very weird. McDonald's wanted my data for me to sit in the store, and I was like, I'm not writing down my data on a piece of paper at McDonald's to sit down and eat. I was refilling gift cards to give to homeless people. Anyways, but I was like, why don't I just have an Ethereum app where I can just scan a QR code, and then while I'm in the store, they can have my data. Okay, they can have like maybe my name, my Ethereum name, and stuff like that. But then when I leave the store, I remove access to that data. I feel like like having hash tables and Bloom filters of data, and then being part of someone's mesh with your data, and then removing them from your like having access will obviously be soon. Anyways, total tangent. Then you get into the difficulty of the block, which is calculated from the previous block's difficulty and its timestamp. So this gets kind of confusing, I guess, but when calculating a block's difficulty, it's an algorithm that uses the previous block and then how long it took, and then it tries to be like, okay, if this block was mined too quickly, we're going to increase the difficulty, make it harder, and if that block took too long to mine, we're going to make it easier. So that's about it. The number is the quantity equal to the number of ancestor blocks behind the current block. So what's the block number? So it ticks up by 1 each time. Gas limit is the quantity equal to the current maximum gas expenditure per block. So I think the gas limit right now is about 12,500,000. I guess the argument is why not just keep increasing the block limit of the gas limit because you can add more transactions to the block. I'd say the most people argument right now is like a lot of miners would like that because if you get more transactions, you get more gas prices and you get more gas fees. And a lot of application users would like that because obviously, not obviously, but if you increase the amount of block space you have, you can get more transactions in for less price, and therefore gas fees would go down. It's not actually how it necessarily works out. Also, you got a lot of like uncles and like other issues. So a lot of like the protocol developers don't want to increase the gas limit too quickly because a lot of basically security issues. Like that's it, security. But for example, like a lot of these proofs for layer two solutions require so much gas, like for example, like 5 million gas per proof. And so if the gas limit per block is like 12 million gas and you have 5 million gas per proof, it'll take 2 or 3 blocks to get your proof in. Therefore, how usable is your layer two solution is now another problem people have. Anyways, you have your timestamp. That's how you know when that block was created. That's how you figure out the difficulty and all that stuff. Extra data. So the extra data contains extra data, and usually this is where people put flags, I guess. So this is where you can put like, so when I was in the ETH2 testnet, the way to get a POAP to show that, oh, I did the testnet. I don't think I got one because that was so busy for me. Anyways, I put my flag as like marmaj.org because I was like, okay, well, it's kind of cool. If I find a block, it'll show up as a flag and it'll show, okay, marmaj.org found this block. When I eventually do have my validator running on ETH 2.0, eventually I will have my flag as marmaj foundation or .org or something, but that's where that would go. And that's where you can kind of put, you can be like, oh, I found this block, or you can kind of do a lot of cool things with the extra data. Mix hash is a 32-byte hash that verifies a sufficient amount of computation has been done on this block. And then this is where I think, I'm pretty sure this extra nonce is only for extra data. So basically, if the difficulty goes so high that it goes above this 32 bytes, you have an extra 8 bytes of which to add in extra difficulty. I think it's something that was taken from Bitcoin. I don't think Bitcoin ever got to a point where it needed this extra data, but I think Ethereum still has this extra data part included. Anyways, that's it for, oh, sorry. And then you have the Overblock headers. These are the Overblock headers, 15 components listed above of this block. So you have like the block headers of all these things all in one component. And then you have the transaction series. This is a list of transactions in this block. And this is where the really big fun part comes in, like recently, where you're talking about like MEV and like miner extracted value, and like, if you can order transactions differently, you can, if you're trading, for example, it's like front running. They're calling it front running, I guess. I don't know. I don't really care about the politics of it too much. But the idea is, if an order is coming in your miner, and a big order is coming in to buy some ETH, right? You can order the transactions to put your order in front of it to buy a bunch of ETH first, and then put their order in, and then right after that you can sell all the ETH you bought, right? So obviously you'd buy some ETH, you put in their big order to buy a bunch of ETH. Then you would put an order right after that to sell your ETH on the next block, for example, and then you would have if you're the first person in the next block to sell, you're getting the best price. And obviously, if you're the one in charge of ordering transactions, you're always going to order transactions to make sure you have the best price. Then with flash loans involved, where you can like borrow any amount of money in one transactions and order it's kind of an unfair advantage, people say. I mean, you could just become a miner and do it yourself, I guess, is what I would say to that, I guess, for now. Who knows, though? A lot of research being done on it right now, a lot of very cool papers coming out about it. I'm just learning and reading. I'm not really putting too much of an opinion on it. In my opinion, we're moving to Ethereum 2.0. We're moving to rollups. We're moving to layer 2 solutions, to sidechains. If miners want to get some more value for the job they're doing, they should. They secure the entire network, and so if they find some value to extract somewhere, go for it. If I can go trade my assets somewhere at a price, because when you trade on Uniswap, for example, you can set your maximum slippage. And so if I can set a price and I can know that my order won't go through if that slippage is hit, that is secure enough for me to know that at least the worst that happens to me is gas gets wasted. If I'm going to be picky or greedy and try and make a lot of money out of something, then maybe I'll get burned by a miner who wants to make some money too. That's capitalism, right? World we live in. But yeah, anyways. 2.3.3, block number and difficulty. This isn't that. Anyways, note that it is difficult. Note that is the difficulty of the Genesis block. I don't know why it says that. Anyways, the Homestead difficulty parameter is used to affect a dynamic. Oops, I disconnected for a second. I'm back. Of time between blocks. As the time between blocks varies, as is discussed below, it is and as implemented in the EIP2, in the Homestead release, the exponential difficulty symbol caused. Okay, this is actually not that important. I'm not going to read this whole thing. This is just explaining like how difficulty has been changed over the years. Who cares? Basically, difficulty can be changed and adjusted now, and there's a difficulty bomb set in to push towards going to Ethereum 2.0. I don't care. Account creation definitely occurs with contact. Definitively occurs with contact creation. Is related to init. Lastly, there is the body, which is the EMV code that executes if when the account containing it receives a message call. So that's just whether you're creating a contract account or a normal account. Account state. The account state contains details of any particular account during some specified world state. The account state is made up of 4 variables: the nonce, balance, storage root, and code hash. So the nonce is the number of transactions you sent, or the number of contract creations, but that's like the same thing. Like it's a transaction you sent to either send or send ether or send some token, or to interact with a contract or create a contract. Same thing. Transactions increase your nonce. Starts at 0, ticks up from there. I guess can go up to not infinity, but like a really, really high number. Balance is the amount of way owned by this account stored as a key value pair inside the state database. That's what we're talking about. You count to value. So you're just a mapping to like your balance, your account to your balance of ETH. So every account has a balance of ETH. It can be 0, but that's why like ETH is not the same as ERC20 tokens. Now, even when you're coding them, they're not the same. Even when you use like Uniswap, you have to have wrapped Ether, and that's because Ether is built in at a base level, whereas ERC20s are something built on top of it, like as contracts. So they still up your nonce, but they're different. And you have your storage root. This is the hash of the root node of the partition tree that encodes the storage context of the account. So here on this little A, I think you're going to say this is for a particular path from root to leaf in the state database. So to make it very clear, from the root of the entire state, which we talked about, would be found here in every block, all the way down to the very last leaf would be the storage root. So every single account has a way to get through that very quickly and easily, which is obviously important. And you have the code hash, the hash of the EMV code of this account's contract. I would assume this is only for smart contract accounts because normal accounts wouldn't have code. But code hashes are stored in the state database. Code hashes are permanent and they are executed when the address belonging to the account receives a message call. Okay, then you go into Bloom filters. The Bloom filter is composed of indexable information, logger address, and log topic containing each log entry from the recipient of each transaction to get. Okay, anyways, Bloom filters. Processing and computation. This is where we get into the fun stuff, I suppose, past like how the data structure, how it's done, into how we actually process things and compute transactions on Ethereum. So the basic method for Ethereum accounts to interact with each other. The transaction is a single cryptographically signed instruction sent to the Ethereum network. Okay, so very basic. That's all a transaction is. There are 2 types of transactions, okay? A message call and a contact creation. Transactions lie at the heart of Ethereum and are entirely responsible for the dynamism and flexibility of the platform. So in order to do anything on Ethereum, you need to have some sort of transaction in order to interact with the state. Transactions are the bread and butter of state transitions, that is of block addition. So in each block, you have all these transactions, and then you add to the next block. If your block's empty, it doesn't add to the state, and therefore nothing's happening. Each transaction applies the execution changes to the machine state, a temporary state which consists of all the required changes in computation that must be made before a block is finalized and added to the world state. So now you're getting to two different states, right? You have like the machine state, which is everything that's happening really quickly to change the world state. And that's kind of what you have. So you have all these transactions that are going to change this machine, that are going into this machine state, which are then going to be finalized and impact on this world state every 15 to 20 seconds for each block. La di da di da. Then you have transactions root. Notation is the list hash. Alternating transactions root. So, anyways, description of it. It's the KEKAC 256 hash. Again, that's just a hashing algorithm that Ethereum uses, similar to SHA-3 for, I guess, Bitcoin uses SHA-3, I think. Geez, look at me trying to remember hashing algorithms. Of the root node that precedes the transactions in the transactions list section of a block. So basically, if you're going to have a transactions list and you have a hash to prove that these transactions are supposed to be included. So it's very easy to prove. For example, if I take all these transactions in the transactions list and I can hash them on my computer, and if it's not the same hash as this transactions root, I'll be like, this is wrong. Now, I might not know exactly how to fix it, but I can know that it's wrong, and then I can at least figure, okay, this is not something I should sign. This is not something I should, like my client should not. So for in Ethereum 2.0, for example, if I sign something wrong, I get slashed and lose some of my stake. So if I knew that I can compute the transactions, I know someone's trying to sneak something in, I can slash it. And then you could obviously use cryptography to figure out where that data came from, trace it back to who sent you that data, and then be like, oh no, I didn't do that. This person sent me this bad data. Let's slash them. And you can prove they sent it to you. Then everyone could be like, yeah, slash them. And I guess that's how that's how you actually prove these things with cryptography. So yeah, the nonce, number of transactions sent, the gas price, gas limit, to value, and then VRS. VRS confuses some people, but don't even worry about it because it's not that important. So the nonce starts at 0 and it's the number of transactions sent. Gas price is the number of way to pay the network for a unit of gas. So I think of it as like a gas station, like a real gas station on a car, as your transaction driving somewhere. When you go to the gas station, you see a price for gas, but depending on the kind of work you're trying to do in your vehicle, like you're gonna have a different like gas limit. So certain vehicles, might be huge, Hummers or carrying a huge trailer, and so they might take a lot of gas to do what they need to do, but they also might use a lot of using a lot of gas. So I think there's like multiple things to think about when it comes to gas prices and gas limits and what the transaction you're doing. There's the price of gas currently, which is like the average price of being included in the block. So that's what gas price will I have to pick for a miner to probably choose me. So this is why I'm excited for EIP 1559. Not because it'll save any gas, but only because if I submit a transaction, I want it to go through in the next block. I don't really care about the price too much. But if I look at my computer and I see the 200 Gwei, I want to know if I pay 200 Gwei, it'll be in the next block. If I pay 150 Gwei, it'll be in 2 blocks around. And I should know around how many blocks based on the price. Right now, it's just an auction, so you can pay a certain price and not have any clue when it'll really get in, because you could submit a transaction. Let's say a block explorer tells you, okay, the average for the past 50 blocks is 50 Gwei. So you put that in, but then the very next block could be 70 Gwei, and so your transaction will never get included. And I think that's obviously a very large user experience issue for any blockchain, but especially for Ethereum. And I think I'm excited for it to get better and change. But with that, you have to choose the price of 50 Gwei, but then you have to choose, okay, well, is it a simple Ethereum transaction? That's 2100 gas, I think. Or are you doing like a smart ERC20 call, which is, I think, double, minimum, because they got to wrap it and do some silly things with ERC20s. Or is like a smart contract call. You have 200,000 Gwei is what you need, or whatever, to spend. So now you got to think about the price, but also how much gas you need, and then the weight of the work you're trying to do, it gets kind of confusing. But luckily, the clients will all like when you try to send a transaction on Ethereum, they'll estimate all that, well, not estimate, they'll calculate all that for you beforehand, and so the gas limit is almost, well, in a client is always estimated or given for you, and so is the gas price. It's at least estimated for you. So the gas limit can be calculated by using the opcodes in the transaction, and you could know the exact amount of gas beforehand that you need. So imagine you're going on a camping trip and you know your car very well, and you know you need 100 liters of gas to get somewhere. But what you might not know on the day of your trip is your gas price, right? You might not know on the exact day of your trip how much gas, like what gas is going to cost. So today gas was 99.999 cents. Tomorrow might be $1.05. So you might not know exactly what that's going to be. That's where gas tokens can help, where you can mint gas tokens. You can have a bot, for example, mint gas tokens every time gas is at, let's say, 50 Gwei. So that's where, it's almost like every time you look at the gas price at the gas station, every time it was at $1, you bought a bunch of barrels. So that when you go on your trip, you knew exactly how far you had to go, and you knew exactly what the gas price would be. And for trading, that could be helpful because, if you know you want to make a certain amount of money in your trades, and you know exactly how much you purchased your gas for, then the math used to do your trading will be simpler. Then you have where you're doing the transaction. So if you're in the car analogy, where you're going for this trip, which would dictate, limit and how far you're going to. I suppose for this. And then the value, the number of Wei to be transferred. I guess the value doesn't always have to be anything. I guess you could always have a call to something that doesn't actually have any Wei transferring value. So that could be 0. And the VRS are just the values for signing. So nothing that someone who just interacts with the blockchain has to worry about too much. This is always taken care of by like Truffle, or just every platform you use takes care of this for you. But it is very important to know that there are cryptographic values that you have in your private key, that you use to sign transactions, to ensure that someone can know that you are actually the person that's supposed to be signing this. And that's how it will go into to make sure that this transaction was supposed to be put together. So it's a valid transaction. State transition function. State transitions come through the state transition function. This is a high-level abstraction of several operations in Ethereum which compromise the overall act of taking changes from the machine state and adding to the world state. So I guess this is where you have that state. Oh, I was talking to Danny Ryan today about hopefully getting more involved in like Ethereum 2 research, Ethereum 2 coding, all that kind of stuff. And so I actually posed a question to the status AMA because Vitalik was in there or whatever. And they actually asked my question, which was really cool. And my question was like, okay, I see all these like ways to get involved with Ethereum, like as a dApp developer or like to build applications, but I have no desire to build anything. I've kind of tried, and I have no motivation for that. But getting involved with the research or the networking layer of Ethereum or anything like that is really cool. It's really fun for me. So I was like, how do I really get involved in becoming either a core developer or like a researcher for Ethereum 2.0? And so about core development, his answer was potentially write your own Ethereum or Ethereum 2 implementation. So I was like, I have no clue how to do that, but let's go. Sounds like fun. But when I was talking to Danny Ryan about it today, he was saying that that's a very complex and very big task to take on, which I still might do it. But he was saying potentially start with optimizing a state transition function. And so this is, I guess, going. I didn't get to the full paper today at the dog park. I stopped around here actually. So kind of cool that I'm doing this live. But I guess this would be that what I was just talking about we're taking that machine state. So you go, okay, these are all the valid state transitions that are supposed to be happening on Ethereum. And then how do you actually get them to happen? Like, how do you actually do them in an efficient way? So what Danny Ryan was talking about was potentially working on making it more efficient the way it already happens. So I'm definitely going to look into that. But that's what this is about. And mining, I disconnected again, but I'm sure I'll be back. It always comes back soon. Yeah, there you go. I'm back already. No data. This stream will end shortly unless you restart it in your streaming software. I don't know. It's saying I'm not streaming right now. Oh, there you go. It's saying I'm streaming again. Apparently I disconnected. It's very hard for me to tell. Anyways, to mining, the block beneficiary is the 160-bit 20-byte address to which all fees collected from the mining of the block are transferred. So again, you can have a block beneficiary. Yeah, this is a scalar value corresponding to the field of the current block. Okay, so just telling you that you can send the block rewards to an address. Verification. So this is how the Ethereum virtual machine verifies the Omer headers, which are the Omer headers are what is included. Omer block headers include all this information from the block. So verification is the process where the virtual machine verifies all that. The sender function, a description that maps transactions to their sender using ECDSA of the SECP 256K1 curve. So you're just using cryptography to map transactions to who sent them. It's kind of cool. I guess the point of this is to add in something in the base layer of Ethereum that allows you to, always map back to know anyone who sent something very quickly and easily. So serialization, deserialization, this function expands positive integer value to a big endian byte array of minimal length when accompanied by a multiplication operator. It signals, or maybe it's an addition, like a binary multiplication, whenever we smush things together. It signals sequence concatenation. Multiplication, but of like bytes. So you're like adding them, concatenating them. The big endian function accompanies RLP serialization and deserialization. So I guess again, more ways to optimize or to make it more efficient to look up information. The EVM. The EVM is a simple stack-based architecture, or has a simple stack architecture. The word size of the machine, and thus the size of stack, is 256-bit. This is chosen to facilitate the KEKAC 256 hash scheme and elliptic curve-based computation. The memory model is a simple word addressed byte array. The memory stack has a maximum size of 1004 bits. The machine also has an independent storage model. This is similar in concept to the memory, but rather than a byte array. It is a addressable word array. Unlike memory, which is volatile, storage is non-volatile and is maintained as part of the system state. Okay. All locations in both storage and memory are well defined initially as 0. The machine does not follow the standard von Neumann architecture. Rather than storing program code in generally accessible memory or storage, it is stored separately in a virtual ROM, interactable only through specialized instructions. So those opcodes come in. The machine can have exceptional execution, so things can happen outside of what you expect, only through for several reasons, including stack underflows and invalid instructions. Like the out of gas exception, they do not leave state changes intact. So this is where, I guess the best way to explain this is like a flash loans, where you can borrow any amount of money on Ethereum and all these protocols in DeFi. But only if you pay back the loan in the same transaction. So this is kind of explaining this whole you could kind of work through all this logic and all these state changes in Ethereum, but unless it's like valid, it'll just revert everything to where it was. So like if you expect something to happen, it'll go through it up until you get to an exceptional execution. Like something like out of gas, or something like, oh wait, you didn't pay back this loan in one transaction. But if you try and call a function with not enough gas, it'll like try and go through the function, which pay, and then it'll be like, oh, you don't have the fees, which I guess are coming up next, and so it'll revert that transaction. It'll halt immediately and report the issue to the execution agent. So either the transaction processor, you, or recursively the spawning execution environment, which will deal with it separately. Okay, so fees, this is where we're getting into the fees, are denominated in gas, are charged under three distinct circumstances. All three are as prerequisite. It's okay, Mika. It's okay, baby. You heard something? It's okay. I know. I know. The first and most common is the fee intrinsic to the computation of the operation. So that's just a fee to perform a transaction on Ethereum. Secondly, gas may be deducted in order to perform to form the payment for a subordinate message call or contract creation. So, I mean, yeah, when you create a contract, you got to pay. Makes sense. I guess they're just separating out transactions from contract creation. I've always considered like a transaction just to be any transaction. Anyways, it's fine. This form is part of the payment for the create, call, and call code operations. Finally, gas may be paid due to increase in the usage of the memory. Don't know what that means to be. Maybe like just to speed up your transaction, but that's not just to pay a miner. I don't really know what that means. Maybe to increase your contract storage. Not sure. Over an account's execution total fee for memory usage payable is proportional to the smallest multiple of 32 bytes that are required, such that all memory indices, whether from read or write, are included in the range. So I guess that's just, you need to make sure you're paying enough to store everything in your contract in 32 byte multiples. So like this is actually where it's actually pretty important to, well, this depends what you want to do, but to save gas, you should make sure that like when you use variables, you're using them in 32 byte multiples. So if you have a variable that only uses like 16 bytes, you should add it in to use to another 16 byte variable, or you can like take a 32 byte variable and split it into two 16 byte variables. But that can be a way in which you can save gas. Due to this fee, it is highly unlikely just within the above. Okay. This is paid for on a just-in-time basis. As such, referencing an area of memory at least 32 bytes greater than any previously indexed memory will certainly result in an additional memory usage fee. Due to this fee, it is highly unlikely that addresses will trend above 32-bit bounds. I guess this is talking about specifically for addresses. Like, why would you ever want to have an address later on? Just make a new address later. For smart contracts, implementations must be able to manage this eventuality. Storage fees have a slightly nuanced behavior to incentivize minimization of the use of storage. So yeah, this is just kind of talking about pricing opcodes or pricing storage on Ethereum. They're trying to price things so you don't use Ethereum for storage. Like you should not be using Ethereum as a place to store things. It clogs the network. I've been reading a bit about this actually. This is super. I wish I could like highlight it, and like this is super interesting to me, and I've been reading about it for a while, and I want to read more into it. So, where are we? Yeah, so I'm just reading from the beginning because I think it's really interesting. Storage fees have a slightly nuanced behavior to incentivize minimization of the use of storage, which corresponds directly to a larger state database on all nodes. So the more storage that's used that one person uses, because every node has to hold the state of Ethereum, the storage that everyone has to hold is larger. So there's an incentive to reduce the amount of storage on Ethereum. Okay, so the execution fee for an operation, okay, that clears an entry in the storage is not only waived, but a qualified refund is given. Okay, now this confuses me because in my opinion, blockchain, things always cost money. Okay, to use the blockchain, it costs money. But this is saying that not only is the fee to use the blockchain waived, okay, but they're going to pay me in ETH. The refund is effectively paid up front. So I can get an upfront payment of ETH. I don't know, man, apparently. for clearing out storage in contracts. Okay. Since the initial usage of a storage location costs substantially more than normal usage. Okay. So I guess what they're saying is my normal call to do something is always going to be less gas than removing that storage from the network. And because it's always that way, as long as I can determine, like to prove that I'm going to take some state and put it to zero, they're going to give me some ETH. I got to figure out how to do this. I want to do this. How do I do this? How do I take smart contracts and then remove the storage in them? I have an idea of where this is very possible in my mind already. I think someone's already doing this on mainnet right now and making money off of it. So I think I want to try doing it. It seems like it should be easy. I should be able to just call a function that zeroes out the storage of a contract. Anyways, we're gonna move on. But like, that just seems like a way I can just make some ETH. You know, for the foundation, obviously. Like, I want to raise money for the Mama J Foundation. If I could help to reduce the storage that every single node has to hold on Ethereum, and get paid ETH that I will use to run an ETH2 node for the foundation. But it seems like I can get paid for that. I gotta look more into that. That's a project. I'm busy. Anyways, next, execution. The execution of a transition defines the state transition function. STF is, I guess, how you'd see it in the code. However, before any transaction can be executed, it needs to go through the initial tests of intrinsic validity. And this is where I was already talking about most of this, but 3.8.1 intrinsic validity. The criteria for intrinsic validity are as follows. The transaction follows the rules for well-formed RLP, recursive length prefix. So basically, does it follow the rules for something I can go look up, right? If it doesn't follow the rules, we're not going to execute the transaction. Is the signature valid? So that's where we went to the whole VRS thing. We were signing something. Did you sign? Was it signed properly? The nonce is valid, so we start at zero, we go up from there. Is this the correct nonce? Has it been used before? And the sender's account balance contains the cost required up front. And this is kind of the whole validity thing. Everything's up front in Ethereum or in blockchain. So if you don't have the money at the time you do the transaction, it'll fail, revert, whatever. It won't go through. Transaction receipts. This is, while the amount of gas used in the execution and the accrued log items belonging to the transaction are stored. Information concerning the result of a transaction's execution is stored in the transaction receipt, TX receipt. The set of log events which are created through the execution of the transaction log set, in addition to the Bloom filter, which contains the actual information from those log events, logs Bloom, are located in the transaction receipt. In addition, the post-transaction state, transaction state, and the amount of gas used in a block containing the transaction receipt, post gas used, are stored in the transaction receipt. I think this is supposed to be written like this. I should probably tell them. I'll tell them later. I might put my own little pull request and update that. And this is where I record it, because later on when I watch this back, I'll remember that I forgot to do this. I forgot to tell them probably, and I'll do a little GitHub pull and help. But as a result, the transaction receipt is a record of any given execution. So basically, anytime you do any execution on the EVM, you will get a transaction receipt, which gives you all this stuff, so you can always prove that there was some validity in that execution, which is this part, the verification part of everything. Yeah. Okay. Lots of reading. Very fun. A valid transaction execution begins with a permanent change to the state. The nonce of the sender account is increased by 1 and the balance is decreased by the collateral gas, which is the amount of gas a transaction is required to pay prior to its execution. The original transactor will differ from the sender if the message call or context creation from a contract account executing code. That's just saying that if you're executing code yourself, then the sender is you. But if a contract's executing code, the sender is from the contract. After a transaction is executed, there comes a provisional state, which is a pre-final state. Gas used for the execution of individual EVM opcodes prior to their potential addition to the world state creates provisional state, intrinsic gas, and an associated substate. The account's tagged for self-destruction following the transaction's completion. This is interesting. This was going to probably help me with what I was thinking about earlier. The log series, which creates checkpoints in EVM code execution for front-end applications to explore, and is made up of the log set. Needs to be a space. I'm going to go through and do some editing, probably of this PDF, because stuff like that's going to bother me. A little bit of OCD, but I don't mind helping, so why not? And logs bloom from the TX receipt, the refund balance, and the refund balance. So this is what I'm talking. The refund balance. What's this? The S-store operation increases the amount refunded by resetting contract storage to 0 from some non-zero state. So I gotta call S-store. So I gotta set contract storage to 0 and then call S-store. I guess verifying that 0. I don't know. I gotta figure this one out. I'm going to write it in Python, though, because we're going through some Python tutorials recently, so we're going to write it in Python. That would be so much fun to write a little code in Python that takes contracts and zeroes them out. I have a contract I'm going to test on, too. It's going to be really fun. I'll probably do this project. I'll probably do it live, actually. And I'll probably do it after I finished the Python Viper. Sorry. I'm going to do it in Viper. Sorry, my brain. I'm going to do it in Viper. I've been going through Viper with the Viper.fun thing. I'll put that in the comments because I'm going to forget. And if someone ends up watching this, Viper.fun. But yeah, so the Viper.fun, I've been going through that. And so Solidity is a bit like Solidity is weird. I don't like JavaScript. I don't like Solidity. So trying something new with Viper and Python. Code deposit. If the initialization code completes successfully, a final contract creation cost is paid. So this is kind of giving you the outline of like how you end up paying through things, right? Because you start with, you pay, right? This is the provisional state. This is the gas you're going to pay in the beginning, and then the refund balance. I think it's kind of cool. But then like, if you put a little code deposit in to start, and then if it goes through, you pay that deposit. But if it reverts, you get your money back. So it's kind of like a really cool way of like saving you as the customer, where if you do something silly and it doesn't work, they try and give you this whole like deposit back for, how much it should cost. Execution model, the stack-based VM, which lies at the heart of Ethereum and performs actions of a computer. This is actually an intrinsic runtime that executes several sub-states as an EVM computation instance before adding the finished result. All calculations have been completed to the final state via the finalization function. In addition to the system state and the remaining gas for the computation, there are several pieces of important information used in the execution environment that the execution agent must provide. It must provide an account address, the address of the account which owns the code that it is executing. A sender address, the sender address of the transaction that originated this execution. The originator price, the price of gas in the transaction that originated this. So this is where like things get a little bit confusing because the transaction has an originator and then like you could have like the like transaction sender or the originator of a transaction. And so this is just clarifying to make sure we understand that we are talking about the originator of these executions, not who sent them, or like, you know, because like a contract can send a transaction, but it can still, the transaction can originate from an account, stuff like that. So the input data, a byte array that is the input data to this execution. If the execution agent is a transaction, this would be the transaction data. Account address, again, the address of the account which caused the code to be executing. If the executing agent is a transaction, this would be the transaction sender. The new state value, the value in way, is passed to this account. If the execution agent is a transaction, this would be the transaction value. Again, a lot of these aren't always like, they're different based on if it's a transaction or if it's a contract call or whatever. But code array, the byte array that is the machine code to be executed, the block header of the present block, stack depth, the depth of the present message call or contract creation, i.e. the number of calls or creates being executed at present. And this is where you have like create to and all this stuff, but this is where you get to like, this is for contract creation or stuff. Message call, I guess when you're starting a contract, or like calling a contract. Yeah, cool. And then you have create to, and then call for contracts. Yeah. The execution model defines the state transition function, which can compute the resultant state, the remaining gas, the accrued substate, and the resultant output. Given these definitions, for the present context, we will define it where the accrued substate is defined as the tuple of the self-destruct set, the log series, the touched accounts, and the refunds. This is where we're getting into real fun. Real fun. How much longer do we have? Oh, you know what? This goes straight into Casper. I need to read Casper later on for, we're going to keep, I know it's been, I think it's been longer than an hour. I've been going for an hour and 6 minutes. I'm just going to go through the entire paper so I have it here. Let's see. Here we go. And then I'm going to stop this. I'm going to go through the Casper paper because I need to go through that anyways for the ETH2 Staker Quiz Master Core thing I'm doing. They have a quiz each week, and the quiz this week's about Casper, so we'll do that after. I'm a bit tired. I might lunch or something like that between that, but a long day. The execution function is most practical. Implement. Oh gosh, see? Getting tired. Let's go. Let's power through. Let's have some water and power it through. I'm glad I'm finally reading this though. The execution function in most practical implementations will be modeled as an iterative progression of the pair comprising the full system state and the machine state. It's defined recursively with the iterator function, which defines the result of a single cycle of the state machine together with the halting check function, which determines if the present state is an exceptional halting state of the machine and output data of the instruction of the present state is a controlled halt of the machine. What are you talking about, man? I know you're just explaining the execution, but like, this is why I like bullet points. Whenever I like summarize papers, I always put everything in bullet points because I'm like, this block of text is just mind numbing. I mean, I love it. It's like, it's helpful, but you know, an empty sequence series indicates that execution should halt, while the empty set indicates that execution should continue. So if you have an empty sequence or series, execution should halt. But if you have an empty set, execution should continue. Okay. So I guess the set should always be empty, but there should be there should be some sets there, and they should continue. Um, when evaluating execution, we extract the remaining gas from the resultant machine state. It is thus cycled recursively or with an iterative loop until either exceptional halt becomes true, indicating that the present state is exceptional and that the machine must be halted and any changes discarded, or until H becomes a series rather than an empty set, indicating that the machine has reached a controlled halt. What I take from that is that the state machine goes through its own process to go through execution, coming down to a controlled halt. Um, and if it gets to any other halt, it just reverts and then takes the gas from that and doesn't let it go through. If where does it say? It's cycled until, yes, you keep cycling through the gas that is there, because if you have enough gas to go through all the you have enough gas to go execute through the functions. It has that gas, loops through all the functions, I would suppose, until either exceptional halt becomes true, indicating the present state is exceptional, which is not, you don't want exceptional things in blockchain. Exceptional sounds great when you're talking about like, oh, I'm playing soccer and I'm exceptional. No, you want everything to be always the same. So if something's exceptional, because we don't want that, and the machine must be halted, and then any changes discarded. That's where flash loans. If you go through the flash loan and you say we're going to pay back this loan with the end of the transaction, and you loop through all these transactions, you go, oh wait, we're at the end of this, and it's an exception. It's an exceptional thing. It's not what you said it would be. The loan is not paid off. It'll go, okay, discard all those changes back to the beginning. And then, or what has to happen is H becomes a series rather than an empty set. And so what I would assume that means is that this H, I didn't even say what H is. I'm guessing H is in the original paper. Maybe H is a series of hashes or a series of something. But H, this series of a set of things, becomes a series in which, the machine reaches a controlled halt. Because here it says, as long as it's not empty, an empty series, right, indicates should halt. But if H becomes a series rather than being empty set, it should continue. Oh man, maybe I'm wrong here. Maybe it's saying that you don't want exceptional state or no. Yeah. You want a full series. You want a full series. Sorry. I wasn't mistaken. I said it correctly the first time. The machine state is defined as the tuple, which are the gas available, the program counter, the memory contents, the active number of words in memory, counting continuously for the machine 0, and the stack contents. The memory contents are a series of zeros of size 2 to the power of 2, a big number, man. Big number. Execution cycle. Stack items are added or removed from the leftmost lower index position of the series. All other items remain unchanged. The gas is reduced by the instructions gas cost, and for most instructions, the program counter increments on each cycle. For the 3 exceptions, we assume a function J subscribed by one of 2 instructions, which evaluates to the according value. Otherwise, in general, we assume the memory, self-destruct, set, and system state don't change. However, instructions do typically alter one or several components of these values. Provisional state, a smaller temporary state that is generated during transaction execution. Excuse me. Another one's going to come, I swear. But we're going to keep going for now. Message calls. So I think real contracts. A message call can come from a transaction or internally from contract code execution. It contains the field data, which consists of user data input to a message call. Message allow communication between accounts, whether contract or external. Okay, so we get a message call to an external account. Messages can come in the form of message calls, which give output data. If it is a contract account, this code gets executed when the account receives a message call. Message calls and contract creations are both transactions. Okay, so they are transactions, but contract creations are never considered the same as message calls. So I guess that is why they're distinct when we go through papers. Interesting. Message calls always transfer some amount of value. That's why. Whereas contract creation, you could obviously create a contract with zero way and therefore not the same. If the message call is an account creation transaction, the value given takes on the role of an endowment towards the new account. And this is kind of how I've always created new smart contracts. I suppose when I've done it in testing, I've always just created a contract and sent some ether at the start so that when I was doing things with the contract, it already had some ether to start with. But I guess you don't have to do that, so therefore it's the distinction there. Every time an account receives a message call, it returns the body, something which is triggered by the init function. User data input to a message call structured as an unlimited size byte array. Universal gas. Message calls always have a universally agreed upon cost in gas. There is a strong distinction between contract creation transactions and message call transactions. Computation performed, whether it is a contract creation or a message call, represents the currently legal valid state. There can be no invalid transactions from this point. There is also a message call contract creation stack. This stack has a depth dependent on how many transactions are in it. Contract creations and message calls have entirely different ways of executing and are entirely different in their roles in Ethereum. The concepts can be conflated. See, this I've already learned, but I completely forget why. Why are they different? Make them all the same. Message calls can result in computation that occurs in the next state rather than the current one. That makes sense. If an account that is currently executing receives a message call, no code will execute because the account might exist but has no code in it yet. To execute a message call, transactions are required. Oh man. Sender, originator, recipient, count, usually the same as recipient. Available gas, value, gas price, some sort of data, and then present depth of the message call or contact creation stack. We went through that above. Contact creation. To initiate contact creation, you need to send transaction to nothing. So when you send this transaction, recipient being nobody, send to nobody. Yeah. Send transaction to nobody is executed in init and returns the body of a function. Init is executed only once at account creation and permanently discarded after that. So it's a safe way to create an account, and then you can't recreate, can't create over it. Execution environment. The Ethereum runtime environment is the environment under which autonomous objects execute in the EVM. The EVM rem is part of this environment. Big endian function. This function expands a positive integer value to a big endian byte array of minimal length when accompanied by the little, I can't remember the thing's called, binary multiplication or whatever operator. It signals sequence concatenation. Same as before. Gas. Gas is the fundamental network unit. Am I at the wrong spot that I already read? Anyways, if we were to say it again, I'll go through it again. Gas is the fundamental network cost. You need it converted to and from Ether is needed to complete the transaction while it is sent. Gas is arbitrarily determined at the moment it is needed by the block and according to the total network's miners' decision to charge certain fees. And this was kind of interesting because a miner could choose to charge in something other than ETH, so it's kind of interesting. But the miner needs to, like, people need to spend ETH in transactions, so the miner needs to get ETH in that way. But like the miner could choose to spend it's very interesting. Gas is arbitrarily determined. Each miner chooses the gas prices they want to accept and want to reject. So miners can censor whatever they want and choose whatever they want. They can get paid in other tokens or in fiat if they really wanted to. Gas price, gas limit. Gas price is the value equal to the current limit of gas per block according to the miners. Any unused gas refunded to the sender. The canonical gas limit of a block is expressed and is stabilized by the timestamp of the block. Pretty self-explanatory, I suppose. Gas price stability. Where new header is the new block's header, but without the nonce and mixed hash component, D being the current DAG. A large data set is needed to compute the mix hash. A proof of work, and proof of work is a proof of work function that evaluates to an array with the first term being the mix hash to prove that the correct DAG is being used, and the second item being a pseudorandom number cryptographically dependent on it. Given an approximately uniform distribution in the range, the expedited time to find a solution is proportional to the difficulty. Again, just saying that you use this difficulty, difficulty being the current DAG, right? D being the current difficulty. A large data set is needed to compute the mix hash, and proof of work is the function that evaluates the array. You need to prove the correct difficulty is used. The second item is a not really random number, pseudo-random number, but it is dependent on proving that you used this correct difficulty. So if you didn't use the correct difficulty and you found the hash, someone would know. But if you did, you get this, pseudo-random number that anyone could compute based on the correct difficulty and the fact that you found that hash. This is the foundation of security of the blockchain and is the fundamental reason why a malicious node cannot propagate newly created blocks that would not otherwise overwrite history, because the nonce must satisfy the requirement and because its application based on the content of the block. And in turn, its composed transactions creating new valid blocks is difficult and over time requires approximately the total compute power of the trustworthy proportion of the mining peers. Thus, we were able to define the new block header validity function. And all that's saying pretty much is this little paragraph is how the entire blockchain is secured and how we can just know that everything that happened in the previous block did happen, because we know that all the miners had to fight to prove that this was actually what happened. We compute it, and all the miners are agreeing this is what happened. Therefore, and then the longer that time goes on, each new block goes on top of the old blocks, you have more validity and more cryptographic proof that what happened in that block really happened. Gas used, a value equal to total gas used in transactions in this block. So you can see this on Etherscan. You can go to Etherscan and see the amount of gas used in every block. It will not always be 12 million. That's the limit, but the amount used will always be different. Machine state. The machine state is a tuple consisting of 5 elements: the gas available, program counter, memory contents, a series of zeros, memory words, dot count, and stat contents. There's also to execute. The current operation can be executed. Okay, so it goes through each operation one at a time. Makes sense. It'd be really cool if we could have and I guess this is where Ethereum 2.0 comes in, but threading, multi-threading of multiple processing being happening at the same time instead of everything happening at the same time for the same state. Sounds, but I'm very tired. I need to sleep soon. Oh, I disconnected again. Oh, I'm back. I need to get an Ethernet cable. The reason I keep disconnecting is because my Wi-Fi just disconnects for a second. but I'm going to put an Ethernet cable into the Mac Mini soon. Um, Exceptional halting may be caused by forward conditioning causing existing on the stack with regard to the next opcode in line for execution. So if out of gas equals true, you're going to have an issue. If bad instruction equals true, going to have an issue. Bad stack size equals true, you're going to have an issue. And then bad jump destination is true, you're going to have an issue. So then throw exception, else execute the opcode X, then initialize a controlled halt. Seems honestly, seeing stuff laid out like this is so much simpler. All this words at the top, you could have just wrote this, man. I would have. Anyways, exceptional halts are reserved for opcodes that fail to execute. They can never be caused through an opcode's actual execution. The amount of remaining gas in each transaction is extracted from information contained in the machine state. A simple iterative recursive loop with a Boolean value of true indicating that in the run of computation an exception was signaled, or false indicating in the run of computation no exceptions were signaled. If this value remains false, so it's initially false or 0, if it remains false for the duration of the execution until the set of transactions becomes a series, for the set of transactions needs to become a series instead of an empty set. This means that the machine has reached a controlled halt. This is one of the things you can test for. Substate. A smaller temporary state is generally generated during transaction execution that runs parallel to machine state. It contains 3 sets of data. The accounts tagged for self. Oops, I think I'm supposed to have a class today with Web3 Bridge. Well, I guess I'll try and make up for that another time. I do my best to be present in most things, but busy day, busy day. Where was I? The accounts tagged for self-destruction following the transaction's completion, self-destruct accounts. The logs series, which creates checkpoints in EVM code execution for front applications to explore, and has been above the log set and logs bloom from the transaction receipt, and the refund balance. See, I want this refund. The S-star operation usually, okay, but still, so I need to call a function that I guess self-destructs a certain account or address. But so the substate will have my refund balance. That's how I can check what the balance would be for the refund. I want to work on writing this code. The EVM code, the bytecode the EVM can natively execute, used to explicitly specify the meaning of a message to an account. A contract is a piece of EVM code that may be associated with an account or an autonomous object. EVM assembly is the human readable version of EVM code. Assembly, there we go. I went through a little bit of assembly with like Julian Eat the Blocks course. I found it quite interesting. I want to go through it more because it seems like more, I guess, directly what would be happening on the EVM. And I know Starkware has some assembly type code for their Cairo State project, but they're making a Solidity compiler. But I'm like, what about a Viper compiler? Because I'm going into Viper now. But hopefully I'll be able to use Viper to create this little refund contract that I want to make. A really fun project. The canonical blockchain is a path from root to leaf through the entire block tree. In order to have consensus over which path it is, conceptually we identify the path that has had the most computation done upon it or the heaviest path. Clearly, one factor that helps determine the heaviest path is the block number of the leaf, equivalent to the number of blocks, not counting the unmined genesis block in the path. The longer the path, the greater total mining effort that must have been done in order to reroute the leaf. This is just talking about how do you go from a block tree, which is the Merkle-Patricia tree that we've already established that the entire blockchain, one block, is simply a a root, a Merkle tree data structure. So how do you go from that tree, which we agreed is cryptographically proven to be correct, to an actual chain? Is you start linking these trees together based on their roots that go to above, based on the state roots and all that. You have all these roots, all these headers that you could link to each blockchain. And then in order to make sure you have the most secure blockchain, you go, again, I'm disconnecting with my internet. Sorry about that. Internet is back. But to make sure you have the heaviest path, or the heaviest chain, the chain has the most worked on it. That's how you make a blockchain. Fun, fun, fun. Man, we're just going to keep going, eh? Oh, we're almost done. So quickly, akin to existing schemes such as employed in the Bitcoin-derived protocols, since a block header includes a difficulty, the header alone is enough to validate the computation done. Any block contributes toward the total computation or total difficulty of a chain. Thus, we define the total difficulty of this block recursively by the difficulty of the parent block and the block itself. The jobs of miners and validators are as follows: validate, or if mining determined, omers; validate, or if mining determined, transactions; apply rewards; verify, or if mining, compute a valid state and nonce. Sounds complicated. It really isn't. You're just going to validate these things. Omer validation. The validation of the Omer headers means nothing more than verifying that each Omer header is both a valid header and satisfies the relation of nth generation Omer to the present block. The maximum of Omer headers is 2. So again, you're just verifying all this stuff. Transaction validation: the given gas used must correspond faithfully to the transaction listed. The total gas used in a block must be equal to the accumulated gas used according to the final transaction. So, I mean, that would be a pretty big issue. If you went through all the transactions that are going into a block and the amount of gas used was not equal to the gas that was supposed to be used, you'd have obviously an issue there, and like a leak of gas somewhere. Math would be wrong and redo the whole thing. The application of rewards to a block involves raising the balance of the accounts of the beneficiary address of the block and each Omer by a certain amount. We raise the block's beneficiary account for each Omer. We raise the block's beneficiary account. For each Omer, we raise the block's beneficiary by 1, an additional 32 of the block's reward, and the beneficiary of the Omer gets rewarded depending on the block number. This constitutes the block finalization state transition function. If there are collisions of the beneficiary address between Omers and the 2 block Omers with the same beneficiary address, what happens? Or an Omer with the same beneficiary address as the parent block, additions are applied cumulatively. The block reward is 3 ether per block. So additions are applied. I think this is the part that I was talking about, like Ethereum. What happens is when there's collisions, if I recall correctly, they actually pay out people who get close. It's kind of a way to kind of incentivize decentralized mining. So instead of mining all in one big pool and making sure you don't have issues like with collisions, even if you were close, you'll still get paid a little bit. Therefore, mining your own, if you get it yourself, you'll get it, and if you're close, you'll still get paid. State and nonce validation: the function that maps a block B to its initialization state, that is the hash of the root node of a tree of state X. This value is stored in the state database, trivial and efficient, since the tree is by nature a resilient data structure. And finally, defined by the block transition function, which maps in an incomplete block to a complete block with a specified data set. As specified at the beginning of the present work, the state transition function, which is defined in terms of the block foundation function and the transition evaluation function, as previously detailed, There is the nth corresponding status code logs and the cumulative gas used after each transition. The fourth component of the tuple has already been defined in terms of the logs. So you're just continuing to validate the state and the nonce. I mean, I need to go through the actual yellow paper now though, because I feel like it's going to have a lot more of this type of stuff, which will actually make more sense to me than like all these words, which I'm like, show me the code. Show me the code. The end state is given from applying the corresponding transaction to the state resulting from the previous transaction or the block's initial state in the case of the first Byzantium version, whatever. Such transaction otherwise in certain cases there is a similar approach defining each item as the gas used and evaluating the corresponding transaction summed with the previous item or zero if it is the first, giving us the running total. The function is used that was defined in the transaction execution function. Finally, new state exists in the context of the block reward function applied to the final transaction's resultant state. Thus, the complete block transition mechanism, less proof of work, the proof of work function is defined. Man, why are you making all this so confusing? Like, gas use is value of the function is some of the previous items giving the running total. The function is used that was used in the transition execution function. Finally, a new state exists because of the block reward function applied to the final transition resultant state. Thus, the complete block transition mechanism, less proof of work. Honestly, that makes no sense to me. I don't know why any of that's important. Like, just when the state is given from applying the corresponding transaction to the state resulting from the previous state, yeah, man, I get it. Like, they're trying to like be really smart about it, I suppose, but they're saying the state is given by applying the transitions to the state. So you take the state, you apply all these transactions that you verified to the state, like you validate state and nonce. So you take the state at a certain nonce, take all the transactions, apply them to the state, increase the nonce, and this is now your new state. I don't know why you're writing all this words for. Anyways, mining POW proof that a certain amount of work has been done exists as a cryptographic probability statement which asserts beyond reasonable doubt that a particular amount of computation has been expended in the determination of some token value, POW token. It is utilized to enforce security of the blockchain, since mine blocks, which reward the proof of work, also serves as a wealth data mechanism. For this reason, the proof of work function is designed to be as accessible as possible to as many people as possible. Simply stating that the proof of work mechanism is a way to efficiently and cryptographically prove that you've distributed assets to people who are securing the network. A very basic application of this principle of accessibility is found. I disagree. This is so stupid. How is this accessible? How is, like, okay, literally 2017, I had a bunch of money in crypto and I wanted to be an Ethereum miner because I thought it was cool. I wanted to help the network. Where am I supposed to mine? Even if I have all this money, it is not accessible. I'm sorry, to have mining proof of work. I don't care what anyone says to me. Bitcoin is not accessible. Ethereum 1.0 is not accessible at all. It'll start to be accessible when you get to proof of stake, if it works. And so, anyways, I am not going to read this because this is just talking about F hash and the F hash proof of work algorithm. The exact same as in Bitcoin. It's very simple, but I will go through here. Ethash is the proof of work algorithm which was used to launch the Ethereum network and bring it through its first few releases. It is in the process of being gradually phased out and replaced with a proof of stake model. For now, it is the latest version of Dagger Hashimoto, introduced by Vitalik Buterin. The general route that the algorithm takes is as follows. There exists a seed which can be computed for each block by scanning through the block headers up until that point. From the seed, one can compute a pseudo-random cache that is cache init bytes in initial size. Light clients store the cache. Okay, so light client would have this cache. From the cache, a data set is generated, data set size bytes in initial size, with the property that each item in the data set depends only on a small number of items from the cache. Basically, meaning you could look up data from the cache without having to have all the data. You only need the block, the nonce, the block header, some different header information. Full clients and miners store the entire data set. The data set grows linearly with time. This is why, reducing the state of Ethereum is important so that it wouldn't actually necessarily, well, it would always grow, but maybe you could reduce a lot of data from Ethereum. I think the number was not that much actually, but still. Mining involves grabbing random slices of the data set and hashing them together. Verification can be done with low memory by using the cache to regenerate the specific pieces of the data set you need. So if you want to verify something was correct, you take specific pieces of the data you need, you hash them together, and because you're hashing them, you can just be like, okay, this data should equal this hash, right? It should equal 0, let's say, or equal this. And then if you hash, right, and you get something other than this, it's incorrect. And then you could obviously go in and dig deeper and go through and find things. Yeah. Mining involves grabbing random slices of the data, mashing them together, verifying that. The large data set is updated every one epoch, 10,000 blocks. So the vast majority of a miner's effort is spent on reading the data set rather than making changes to it. The difficulty mechanism. Okay, now we're getting into anyways. This mechanism enforces a relative predictability in terms of the time window between blocks. A smaller time period, the last 2 blocks, results in an increase in the difficulty level and thus additional computation required, lengthening the next time window. Conversely, if the time window is too large, the difficulty is reduced, reducing the amount of time to the next block. The total difficulty is the difficulty state of the entire Ethereum blockchain. The block difficulty, in contrast, is not a state of the blockchain, but is local, particular to each specific block. You reach the total difficulty by summing the individual difficulty of all previous blocks and adding the difficulty of the present block. Total difficulty is all difficulty of Ethereum ever, and block difficulty is the difficulty of the current block or potentially the next block that you're going to be in. The Ghost protocol provides an alternative solution to double spend attacks from the original solution in Satoshi Nakamoto's Bitcoin white paper. The Nakamoto solved the problem of double spending by requiring the network to agree on a single block in order to function. For that reason, in the Bitcoin protocol, it is impossible to submit a double spend block without having at least 50% of the network's mining power to force the longest chain. This is because the network automatically chooses the longest chain. So even if one wanted to submit 2 spent transactions in a row, the network simply picks whichever one comes first, ignoring the second one because it no longer pertains to the longest chain, which now consists to the first block that was sent. So the would-be hacker needs to submit a new block as the first double block is no more feasible. Basically saying that in Bitcoin, if you want to submit a double spend, let's say I spent 10 Bitcoin in a transaction, everyone saw it, it's mined upon, and I spent that money, I got my Lamborghini, I got my car, good job. What they're saying is that if I tried to spend that Bitcoin again somewhere else, I would need to convince the entire network to revert to that new chain. And if I can do that, that's going to cost a lot more than Bitcoin, and go for it, I suppose. And that's why you got the other, you have your 6 Bitcoin confirmations before something is finalized, because when something happens in one block, it's final for that block, but the more blocks that happen after it, the heavier the weight and the more final the block that you are looking at is. So after about 6 Bitcoin blocks have been mined, so 6 confirmations, most people feel really confident that whatever is in this block mined on top of it, is relatively secure. So the Ghost Protocol, which stands for Greedy Heaviest. Ghost Protocol stands for Greedy Heaviest Object Subtree. Rather requires that miners begin mining whichever chain is the most miners are on. Okay, because of differences. Yeah, see, my network is having its own fair share of issues for no reason. Yeah, sorry, I'm having network issues. This constitutes anything based off the factor that are unknowable under regular pseudo, but become knowable through regular operation of. Okay, so a pseudo-random number is any number that is random, like currently, but is not random anymore once you actually look at the chain. So, for example, when you use like the block difficulty to give you a random number on chain, for me, knowing the block difficulty of the next block is random, right? I don't know the block difficulty currently, but when the next block happens, I'll know it. So that's how you kind of use a number that's pseudo-random. It's random before we know about something, but it's not random after. Let's see. It's still saying my stream isn't working. Let's see if I refresh this page, what I get. Because I should still be streaming. Okay, yeah, I am streaming. It is working. Cool. Chain size limits. The state database usually won't store every single tree structure in the history of the blockchain. One idea has been proposed to simply maintain node checkpoints for each age, 10,000 blocks, and eventually discard checkpoints which no longer contain necessary. This is the idea where you would start cutting out certain parts of the database, but we'll see if that actually happens. Scalability. Scalability is a constant concern because Ethereum state transitions are so broad in terms of possible content, and because its applications and use cases are so enormous in the number of potential transactions required. Scalability is inherently necessary for increased transaction throughput and more efficient storage and traversal of the chain. Sharding, parallelization of transaction combination, and block building. So this is what's coming in Ethereum 2.0, hopefully. You get into Casper and then Plasma. So Plasma chains is, I think, what you look in when you see Matic currently, and I think other sites are using Plasma. Casper is a new, I think PubSub, like a way in which you discover other nodes in Ethereum 2.0. I don't think they're using Casper now, or they're using some other way of doing it now. No, they use Casper. Darn it! I know Casper's using Ethereum 2.0 and sharding. So that's all for. Oh, then you have the opcodes. If you want to read through all the different opcodes for Ethereum, I'm not going to go through all the opcodes. There's a ton of them. You can read through them. You probably should, and the references. So and the glossary and all that kind of stuff. So if anyone wants to go through this paper themselves, I put in the comments the 2 links for the GitHub to get to it. Please feel free. I hope you enjoyed, or if anyone ended up watching this. But yeah, that's about it. A 2-hour nice little live stream of me reading through the Ethereum Beige paper. Yeah, not too complicated of a paper. I will go through the yellow paper eventually as well on here. But the next stream I'll do on here will be hopefully today, going through the Casper paper. Actually, maybe it'll be here, and maybe I can just click it. Cancel. Probably not, eh? I probably won't be able to just click the Casper paper. But we're going to go... That's not how we're going to find it. Anyways, I'm going to end this stream. Thank you very much, everybody. Hope